Welcome everyone. Today, we'll discuss non-destructive examination, or NDE, as outlined in API 577. These techniques allow us to inspect materials and welds without causing damage, which is critical for safety and reliability in industries like oil and gas. NDE is a cornerstone of quality assurance. It helps us detect defects early, maintain compliance, and prevent costly failures. Let's explore why it's so important. Non-destructive examination or NDE refers to a set of techniques used to evaluate the properties of a material, component, or system without causing damage. According to API 577, NDE plays a critical role in welding inspection and quality assurance in industries such as oil and gas, power generation, and manufacturing. The primary purpose of NDE is to detect discontinuities, verify material integrity, and ensure compliance with safety standards. Unlike destructive testing, NDE preserves the usability of the tested component, making it cost-effective and essential for in-service inspections. NDE methods vary in complexity, from simple visual checks to advanced techniques like radiography and ultrasonic testing. Each method has specific applications, advantages, and limitations, which must be understood to select the appropriate technique for a given situation. The importance of NDE lies in its ability to prevent catastrophic failures, reduce downtime, and maintain operational safety. By identifying defects early, organizations can implement corrective actions before problems escalate, thereby saving costs and protecting lives. API 577 provides guidelines for proper implementation of NDE methods, ensuring consistency and reliability in inspection practices. Before diving into methods, we need to understand key concepts like weld discontinuities and material identification. These form the basis of effective inspection. Discontinuities are interruptions in the physical structure or homogeneity of a material. In welding, discontinuities can occur due to improper technique, contamination, or material defects. Common types include cracks, porosity, inclusions, lack of fusion, and undercut. Cracks are critical because they can propagate under stress, leading to failure. Porosity results from trapped gas during solidification, while inclusions occur when foreign materials become embedded in the weld. Lack of fusion indicates incomplete bonding between weld metal and base metal, compromising strength. API 577 emphasizes the need to identify and classify discontinuities accurately, as not all discontinuities are defects. Some may be acceptable within specified limits, while others require repair. Understanding the nature and cause of discontinuities helps inspectors choose the right NDE method for detection. For example, surface breaking cracks are easily detected by visual or penetrant testing, whereas subsurface defects may require ultrasonic or radiographic examination. Proper documentation and interpretation of discontinuities are essential for maintaining weld quality and ensuring structural integrity. Materials identification is a crucial step in welding inspection to ensure that the correct materials are used according to design specifications. API 577 outlines methods such as positive material identification or PMI, which uses techniques like X-ray fluorescence or XRF or optical emission spectroscopy or OES to verify alloy composition. Proper material identification prevents issues like mismatched metals, which can lead to corrosion, cracking, or failure under service conditions. Inspectors must confirm material grade, heat treatment condition, and traceability before welding begins. This process also involves reviewing material certificates and markings. In some cases, portable PMI devices are used on-site for quick verification. Accurate material identification supports compliance with codes and standards, enhances reliability, and reduces the risk of costly repairs or accidents. It is particularly important in critical applications such as pressure vessels, pipelines, and structural components where material properties directly affect performance and safety. Now, let's look at the main NDE methods: visual examination or VT, magnetic particle examination or MT, alternating current field measurement or ACFM, liquid penetrant examination or PT, eddy current examination or ET, radiographic examination or RT, ultrasonic examination or UT. Each has unique applications and limitations. Visual examination or VT is the simplest and most widely used NDE method. It involves inspecting the surface of a component for visible discontinuities such as cracks, porosity, undercut, and incomplete fusion. VT requires adequate lighting, magnification tools, and surface preparation to ensure accurate results. API 577 specifies that inspectors must be trained to recognize weld imperfections and understand acceptance criteria. VT is often the first step in inspection because it is quick, cost-effective, and does not require sophisticated equipment. However, its limitation is that it can only detect surface defects and relies heavily on the inspector's experience. To enhance reliability, VT is often combined with other methods like penetrant or magnetic particle testing. Proper documentation of observations, including photographs and sketches, is essential for traceability. VT plays a vital role in quality control during welding and in-service inspections, helping to identify issues before they escalate. Magnetic particle examination or MT is used to detect surface and near-surface discontinuities in ferromagnetic materials. The process involves magnetizing the component and applying magnetic particles, either dry or suspended in liquid. Discontinuities disrupt the magnetic field, causing particles to accumulate and form visible indications. MT is highly effective for detecting cracks, laps, and seams in welds and heat-affected zones. API 577 requires proper surface preparation, correct magnetization technique, and interpretation of indications. MT can be performed using yokes, prods, or coils, and may employ visible or fluorescent particles under UV light for enhanced sensitivity. Advantages of MT include its speed and ability to reveal fine cracks, but it is limited to ferromagnetic materials and requires access to the surface. Safety considerations include handling magnetic fields and ensuring proper demagnetization after testing. MT is widely used in industries where weld integrity is critical, such as pipelines, pressure vessels, and structural steel. Alternating current field measurement or ACFM is an advanced electromagnetic technique for detecting surface-breaking cracks in metallic components. Unlike traditional eddy current testing, ACFM provides quantitative information about crack length and depth without requiring electrical contact or removal of coatings. The method uses a probe that induces an alternating current in the material, creating a magnetic field. Discontinuities disturb this field, and sensors measure the resulting changes. ACFM is particularly useful in offshore and subsea environments where coatings cannot be removed easily. API 577 recognizes ACFM as a reliable method for weld inspection, offering advantages such as minimal surface preparation and the ability to operate in harsh conditions. However, ACFM requires specialized equipment and trained personnel. Its applications include inspecting welds on pipelines, platforms, and pressure vessels. The technique enhances safety by providing accurate crack sizing, which supports informed decisions on repair or continued service. Liquid penetrant examination or PT is a widely used method for detecting surface-breaking defects in non-porous materials. The process involves applying a liquid penetrant to the surface, allowing it to seep into discontinuities, and then removing excess penetrant. A developer is applied to draw out the penetrant from flaws, creating visible indications. PT is suitable for metals, ceramics, and plastics, making it versatile across industries. API 577 outlines steps such as cleaning, application, dwell time, removal, and inspection under appropriate lighting. PT can use visible dye or fluorescent penetrants for enhanced sensitivity. Advantages include simplicity and low cost, but PT is limited to surface defects and requires thorough cleaning to avoid false indications. Safety considerations involve handling chemicals and ensuring proper disposal. PT is commonly used for weld inspection, casting evaluation, and detecting fatigue cracks in components. Eddy current examination or ET is an electromagnetic technique used to detect surface and near-surface defects in conductive materials. The method involves inducing eddy currents in the material using a coil carrying alternating current. Discontinuities alter the flow of these currents, which is detected by changes in impedance. ET is highly sensitive to small cracks and can also measure material properties such as conductivity and thickness. API 577 notes that ET is commonly used for inspecting heat exchanger tubes, welds, and detecting corrosion. Advantages include rapid testing and minimal surface preparation, but ET is limited to conductive materials and requires calibration for accurate interpretation. ET can be automated for high-volume inspections and is often used in aerospace, power generation, and petrochemical industries. Proper training and equipment selection are essential for reliable results. Radiographic examination or RT uses X-rays or gamma rays to produce images of the internal structure of a component. It is highly effective for detecting volumetric defects such as porosity, slag inclusions, and lack of fusion in welds. API 577 specifies requirements for film quality, exposure techniques, and interpretation of radiographs. RT provides a permanent record of inspection and allows precise evaluation of defect size and location. However, RT involves radiation hazards, requiring strict safety measures and qualified personnel. Limitations include high cost, time consumption, and difficulty in detecting planar defects. Digital radiography is increasingly used for faster processing and improved image quality. RT is essential in industries where weld integrity is critical, such as pressure vessels, pipelines, and structural components. Compliance with radiation safety regulations is mandatory to protect workers and the environment. Ultrasonic examination or UT uses high-frequency sound waves to detect internal and surface defects in materials. A transducer generates ultrasonic pulses that travel through the material and reflect from discontinuities. The reflected signals are displayed on a screen for interpretation. UT can detect cracks, lack of fusion, and thickness variations with high accuracy. API 577 outlines calibration, scanning techniques, and acceptance criteria for UT. Advantages include deep penetration, immediate results, and portability. Limitations involve the need for skilled operators and difficulty in inspecting complex geometries. Advanced UT methods such as phased array and time-of-flight diffraction enhance defect characterization and coverage. UT is widely used in weld inspection, pipeline integrity assessment, and structural evaluations. Proper coupling, surface preparation, and equipment calibration are essential for reliable results. Additional testing methods. Hardness testing verifies material properties and weld quality. Pressure and leak testing confirms system integrity before commissioning. Both complement NDE for comprehensive assurance. Hardness testing measures a material's resistance to deformation and is often used to verify heat treatment and weld properties. Common methods include Brinell, Rockwell, and Vickers hardness tests. API 577 recommends hardness testing for welds in critical applications to ensure compliance with design requirements. Portable hardness testers allow on-site measurements, providing quick results. Hardness values correlate with material strength and can indicate issues such as excessive heat input or improper post-weld heat treatment. While hardness testing is not a direct NDE method, it complements other techniques by assessing mechanical properties. Proper calibration and surface preparation are necessary for accurate readings. Hardness testing helps prevent failures by ensuring that welds meet specified hardness limits, reducing the risk of brittle fracture or premature wear. Pressure and leak testing or LT verifies the integrity of pressure-containing components such as pipelines and vessels. Common methods include hydrostatic testing, where the component is filled with water and pressurized, and pneumatic testing using air or gas. API 577 specifies procedures for conducting these tests safely, including pressure limits, hold times, and inspection for leaks. Leak detection can involve visual observation, soap solution, or advanced techniques like acoustic emission. LT ensures that components can withstand operating pressures without leakage or failure. Safety is paramount, as pressurization involves significant stored energy. Proper planning, equipment selection, and adherence to standards are essential. LT provides confidence in system reliability before commissioning and during periodic inspections. Accurate data recording ensures traceability and compliance. Digital systems reduce errors and improve accessibility. Documentation includes photos, scans, and calibration records. Accurate data recording is critical for traceability and quality assurance in weld inspection. API 577 emphasizes documenting inspection results, including method used, equipment details, calibration records, and defect descriptions. Digital systems are increasingly used for storing and analyzing inspection data, improving accessibility and reducing errors. Records should include photographs, radiographs, ultrasonic scans, and hardness readings where applicable. Proper documentation supports compliance with regulatory requirements and facilitates future maintenance decisions. It also provides evidence of due diligence in case of disputes or failures. Inspectors must ensure that data is complete, accurate, and securely stored. Standardized reporting formats enhance consistency and allow easy interpretation by engineers and auditors. Comparison of NDE methods. Key takeaways. Non-destructive examination is essential for ensuring weld quality and structural integrity without damaging components. API 577 provides comprehensive guidelines for implementing various NDE methods, each suited to specific applications. Understanding the principles, advantages, and limitations of these techniques enables inspectors to select the most appropriate method for each situation. Proper training, equipment calibration, and data recording are critical for reliable results. By applying NDE effectively, industries can enhance safety, reduce costs, and maintain compliance with standards. Continuous improvement and adoption of advanced technologies will further strengthen the role of NDE in quality assurance.